So thank you very much for the invitation, first of all. And I had a very long title and I made it shorter now. The title is Individualization of Robotic Behavior. And I think this is quite important. And I want to try to tell you in this talk why this is important on the one hand side, and on the other hand side, how can we achieve that? And for that, probably we need state and intention recognition of the human, and we need to enable the systems to learn from that inherently. So I just want to show you some of our systems in Bremen. So I'm working for the German Research Center of Artificial Intelligence, and in Bremen we have the large Institute for Robotics. And you can see that we're mainly do research on autonomous robots. And you can see that they're quite advanced, I would say, and most of them behave autonomously to some degree at least. And that's really the first question that I will bring in my talk is why, or I want to address, why do we need interaction with autonomous systems? So why do we need that? So they're autonomous. So what do we need the human for here? Then I have some further questions, and I will have maybe 3 parts of this talk. So the first talk will give a short overview just for you to see what kind of approaches did we develop in the past that might then later be relevant to know that they are there to understand what I want to give you, tell you in more details. And then I have a second talk that's about challenges for to implicitly infer state and intention from a user when we use EEG, so electroencephalogram. So that's the second part. And the third part, so the third part will be about examples. So I said there are challenges, and then now I want to give some examples how maybe to solve them or to address them. So that will be the third part of my talk. So I will also, if you're interested in the projects that I'm talking about, you can always look them up on our website. So I put that there, and I always will mark a little bit like with this little sign what project we worked on these topics. So you can later on maybe also have a look into those projects if you're interested, and maybe their publication or similar things. So now my first question: why do we need interaction with autonomous robots? So why do we need that? The progressive autonomy of robots is not, or maybe not anymore, sufficient to meet today's requirements for intuitive human-machine interaction. So now is the question why? Why is it not sufficient, or why is it not anymore sufficient? That's a good question. So first of all, I'm more from the science department, so to say. So we want to bring robots to Mars, to Moon, to underwater, and to all these areas where we are far away from the robotic systems. That's why they need to be autonomous, but we still want to have control on the systems. And that's why we need interaction, as you can see here with a robot that was teleported from Bremen in a desert in Utah. There's another example here. This is a robotic system that we built for interaction with astronauts. So it's kind of a little assistant for the astronaut to collect probes. And of course, the astronaut wants to guide the robotic system and to tell the system easily where to go and things like that. So that's why we also need interaction. And this is another example. So this is an exoskeleton that we developed for rehabilitation of stroke patients. And you can see we not only need interaction, but we kind of need collaboration. So we need the system exactly to know what the patient wants to do and how to support best. So, and finally, we also need interaction robotic system to make a robot learn from human. That's just an example. So we don't want to teach everything and write programs for every little piece, but we actually want to interact, and we want that the robot, while interacting with us, to learn how to behave and how to adapt to the needs of the interacting person. And why is it not any more sufficient? Because we had robots in the past, as you all might know, in building cars and things like that. And these robots, they were behind fences. So they were not in contact with humans at all. And even in industry, there is a big change. So they in the future, they might need robots for building more individual products. So each product will be different to some degree, and this cannot be automated completely anymore in the future. So therefore, there is a need to cooperate with the human worker who maybe knows what the next project is all about and what is the next part that's important and so on and so forth. As you can see here, examples. And that's why even in industry, we need collaboration. And that's a big topic since I would say about at least 5 years, maybe even longer. And this was not the case before. And that's why there's also a lot of pressure from industry to go into this direction of research, right? So now we come to the second question. What are the different approaches to interact and devices developed? I only want to give a very, very short overview. If we go into examples that you saw before, calibration, share capabilities, learning, restore function, let's go into the question of when we want to restore function in a stroke patient, what do we need? We need to know from the human what should be supported, how and when. And in general, there are 2 ways to find out. The one way is to tell the system explicitly, tell the system what I need. The other way is the system understands this implicitly. So these are the 2 ways in general, but in principle, both ways are able to tell the system something about the state of the human as well as the intention of the human. And that's why you can approach this in 2 ways, explicitly and implicitly, or a combination of both, of course. So to interact explicitly, you need interfaces. But not only for the explicit interaction, you need interfaces, you also need that for the implicit one, because you want to read data, you want to read brain data, you want to analyze brain data, you want to read mimic gestures and so on and so forth. So you do need technical devices to allow this. And these are just some examples what we developed in the past at our institute. And there are many, many more, right? So this is really, really important. So let's go a bit deeper into the question of explicit intention recognition, and just give one short example that I already introduced before. So this is an example of gesture recognition for the little robot that was cooperating with the astronaut. And since the astronaut, as you saw, he was in this suit and he was really not able to move that much. So we tried to use very rough gestures, such as moving the arm from the one to the other side, to have the robot turn, to get the intention of the robot. He will do this in the next gesture, say intention, and now he changes his commands to actually go backwards, and so on and so forth. So this is a very simple approach. You see this video again, so I don't want to repeat that. And we added some other gestures. So it's very easy to interact with such a robotic systems, like saying like stop and come to me or go away or things like that, just by moving the arms. So this is an explicit way of communication. And just I want to leave it with this example because I want to go more in the direction of implicit interaction next. Implicit interaction also allows us to infer the state and the intention of the human, right? So, but what do we need? What kind of key technologies do we need to build implicit interfaces? Of course, first of all, we not only need technology, as I said before, the interfaces themselves, but we also need concepts and approaches to infer mental states and intention of the user. So there's lots of psychology in it, knowing what it is all about, what I have to look for actually, to know whether he's bored, whether he wants to move, and so on and so forth. And then, of course, we need the interfaces themselves to measure those states, right? And they're, again, different ones. And in general, there are psychophysiological data that tell us something about the human, what the human wants to do next, what the status, and so on and so forth. And to analyze this data, and this might be quite complex, you of course need machine learning, you need AI-based software. This software can be embedded in a system. And maybe you need even special hardware solutions to do that. And then with all this together, you can build interfaces that implicitly allow an implicit interaction collaboration with robots, or also implicit learning from humans. So, and all this has to be close to application. At least that's our goal in our institute. So it's quite hard to bring this all together. First of all, what we did is we, because we also wanted to use brain activity, and we, of course, were aware that since I'm a biologist, that this is not that easy to analyze and use brain activity. We developed an approach that allows us to infer the intention and states of the user under real application conditions. So while you're interacting with robotic system, running around, moving around, and so on and so forth. And we're aware that the signal will be noisy and it will be hard to interpret. And we came up with some general approaches how to avoid malfunction. I will tell about this later. Just want to say that that's very important because you have a false interpretation. And to avoid malfunctions, there are many ways how to enable that, and you can combine all of them. And one thing is to use the context of interaction to know roughly what is all about at the moment. So to say this is very unlikely that he is tired right now because he's very active and running around and so on and so forth, that he's bored, not tired, bored, sorry, for example. Or we can also integrate it into robotics in a systems control. So for example, with the exoskeleton knows when a person is not moving, right? Because he holds still. But, and then when he holds still, you can look for movement intention. So it doesn't make sense to look for movement intention while you're moving around your arms all the time already. So this is also important. And this then can be also adapted to the systems control. There will be an example on that as well. And then of course, what I always argue is that you should not intend to only use EEG data. It makes so much sense to combine it with other biosignals. That doesn't need to be biosignals, can also be signals from the interface itself, from the system itself, and so on. So these are the different approaches, and we actually also modeled that. I don't want to go in details on the model now, because this would also take us quite some time, but that was something we also modeled that quite intensively, how this all is interacting and how to make the behavior safe. So as I said, we can embed it into because we can use other data. So I just want to give this example with the exoskeleton. When we interact with the exoskeleton in a real or virtual environment, we can of course use also eye tracking data. We can use muscle activity of the person. We can use object that the person is attending either in real or in the VR scenario. And we can, of course, also use the position and force measurements of the exoskeleton. We know what the position of the arm is just from the readings of the exoskeleton. So this is something we can all use, right? As I said, we also need software. So to allow a very systematic analysis of brain activity, but also some other time series, not only brain, but for example, muscle activity. We developed a framework that allows us very systematic analysis and benchmarking. And it's actually suitable for both PC, but also for cluster systems, or HPC. And we usually don't have a large PC in a robotic system, as you can imagine. So in the end, we want to have it running on the system. And therefore, we also developed an embedded software hardware solution. So that's that we transferred our software framework PySpace to an embedded CPU and FPGA solution, and we now call it ReSpace. So, and that can be integrated, for example, in the exoskeleton, and can do both. It can control the system itself and can also analyze the biosignals, the EEG signals, and muscle activity at the same time. And that's why it allows a very deep integration into the robotic systems. So, and therefore also into the control of the system. But further, we're also developing on sensor systems, because many people are working on that, but you will always try to get to find alternatives. For example, you could also use ultrasound transducers for recording muscle activity. Or in this example, there was a project where we worked together with a company to develop, on the one hand side, a dry cap system that's very easily to wear, so you can put it on with one hand, dry cap, and also on the other hand, we also developed approaches to analyze EEG data in a cloud system. So this is very important. If you want to bring it to a person at home, you cannot do the analysis at the person's home, so you have to do it somewhere else. So, and that's why the connection to the cloud could be a solution. There might be other solutions, but this was a project where we tried it out, and also especially with the questions of data security and GDPR and questions, and so ethical questions. So this project was trying to find a good solution, and actually did in the end, how to manage that. So then, as I said, we also want to know what the person is doing, and this is a bit out of the scope, so it's not EEG, but it's movement data. And what I show you here is an automated analysis of human behavior. It's ball throwing. You see it in a little figure. And while the person is throwing the ball, there's in this case still Qualys system, so infrared-based system to record the movement. And you can see the red lines. It's just the behavior is segmented automatically, right? So why do we do this? We want to find ways how to analyze psychophysiology data automatically, and that's why I brought this example in here. And that's a way how to analyze it, to find the segments that are important, because when I throw a ball, I don't want to have all the movement, like swinging the arm forward and back is not relevant. It's that moment when you throw the ball that's important. That's what the robot should learn. And this is also a behavior that you can learn in simulation. We usually learn in the system, not in real, but in simulation. But what you can see here is when you learn in simulation, you're way off from what you want to achieve, right? So that's where the ball's supposed to go. That's where it went. And the second trial, you will see the ball goes again somewhere else. Now I have to tell you that this is not really a ball, but it is a bag of rice. So it's a bag of rice. So you cannot simulate it really properly, because it's always changing the shape, and you will, when you go through the video, you see it lands everywhere. So what we do is, while we're learning the system, we try to find solutions, because you can learn different solutions, right? Different way to solve the problem that are very robust in transfer. So this is kind of a transfer learning that we do here, to see what kind of behavior is easy to transfer in the real world. So we don't try to compensate for this big gap between simulation and real world, because we cannot. It's not possible here, but we try to find the solution that is very stable and easily transferable. So, and this can be done with reinforcement learning and transfer learning, is a combination. But that's, in this case, it's quite straightforward, because we have a little goal there, right? This little space and room where the ball should go. And we need this information as a feedback, as a negative and positive feedback, to do reinforcement learning in such a system, to reinforce positive or negative, whether the behavior was good or not, so to say. So, but sometimes this is not given. So for example, you can imagine that's the second example that I want to show you. And that's again with EEG. Here we have a person who wants to interact with a robotic system. The robotic system can do 3 different behaviors, can go to the right, to the left, and can go to the front at the beginning. And the human wants to guide the system with gestures, hand gestures. But the system has no idea about the hand gestures, but the person is just doing one of the gestures, and the system then tries one of the actions to see whether this is the correct one. So normally you could say, give the person a buzzer, say yes, no, yes, no, yes, no, right? But what we do here as a reward is we use the EEG activity as a reward signal, because when the system shows an unexpected behavior, the false behavior, wrong behavior, then in so-called event-related potential, it's the error-related potential, will be evoked in the EEGs, also in the brain, and we can read that in the EEG. And we can detect it as signify and use that as a negative feedback here to learn. So this is a little drawing. You can see that little video. And the special case here is that the system is actually learning both. It's learning to recognize the gesture, as well as it learns the mapping between movement and gesture. So it's not predefined. And that's why you will see that after some trials, we also add a fourth gesture, and that's why this is possible. You can add a fourth gesture, and it will just learn the fourth movement. So the only information it needs is that it now has 4 movements that it's able to perform. And so you can just add additional behavior to learn that. And the other thing is, people tend to show or to explicitly guide a system very correctly at the beginning. So he thinks it's a technical system, I have to speak loud, I have to make the gesture very accurately and things like that. And then usually you have this training phase, and then later it doesn't work anymore, because you start not talking accurately, not talking very loud or precise, or not showing the gesture very precise. But because this is an ongoing learning approach here, the system can adapt. So we really had persons who would change their behavior very much in the end. So we did a video recording and looked at it, and it would still work. Okay, so now these are different things that we did in the past, and I just want to give a summary now about the challenges. And I have some rather general challenges. I'm afraid most of you will know, but I will go through it briefly. So this is when we want to use EEG data. Why do we want to use it? That's the first question. So I could use many signals, right, from the human. But we want to use brain activity because the analysis of brain activity can serve as a window into the human mind or brain. That's from Coles already in 1989. It was very early, before EEG was established. And when we do this, that does even enable us to uncover pre-conscious intention. You might all know the Lipid experiments, for example, right? Where you know already that you want to move before you're actually moving. So, and on top of that, Garrison said the analysis of brain activity is a covered physiological measure that enables permanent access to the human state. So that's also very important, because if you have a person that does not talk to you, then you don't know what to do. You cannot force it. But brain reading is always there, right? Brain signals are always there, like other psychophysiological data as well, of course. And that's also an important thing. So you can see that in general, yes, EEG is very useful for implicit state and intention recognition. And now we do have a problem, right? Most of you might know EEGs and how it looks like. But I should try to get my window back here. Okay, most of you might know that, and you know it is quite noisy, right? Because you have an overlay of activity. It's not only noise; it's the brain is doing so many things in parallel. So it's quite some challenge to read it. The positive thing is that you can record it non-invasively, and the devices get cheaper and cheaper by now. And you have a very high temporal resolution, which is also very helpful. But again, it's very noisy and highly overlaid activity. So if you look into this example, so for example, if you want to read a speller, you probably all know this figure from a speller where you maybe want to choose the O right in the middle. You maybe want to choose the O, and whenever the O shows up, it's blinking up in columns or lines, then your brain will react on that. So you will have an activity in your brain at a certain point. That's the point where the O shows up, and in this window you should have an activity. It's a so-called event-related activity. It's actually called P300. And the problem is that this activity in single trial looks all different all the time, right? So each trial looks all different. So just by eyes, you cannot detect a signal really. So when you do an averaging over many of those trials, then you will see the activity that's hidden in a signal, right? And but this also even requires artifact removal and so on. So therefore, we need some not only artifact removal in some cases, not always, but we also for sure need signal processing and machine learning to learn the signals and to learn to recognize the signals in these single trials that we have here. That's very important. And why is this important? So it's not important for all approaches, and that's why I want to give this little overview here as well. So there are two ways how to use covered physiological data, which EEG is. So one is for active control, the other is for passive adaptation. And the brain activity, if you use it for active control, then this could be the speller. That was the example that I gave you before, right? So we want to see what the O is. And this is an implicit information transfer. So we really have to concentrate on that, and we can implicitly transfer information that we want to choose the O, right? The other example is the passive adaptation. It's called biocybernetic adaptation, passive BCI. There are many different ways how to call it. And this is something like, for example, if the error-related potential, it's an early work of Blankert's, where you, as an example that I showed before, where you can read from the EEG whether there was an error in the interaction or not, and you can use that to correct a system implicitly. So you don't have to tell the system, but you can read that from the brain. And that's more implicit information transfer. And in many cases, for the active control, it's sufficient to use average activity. For a speller, for example, you can average the data like 7 times or so. It's still okay because you can have a good quality of signals, and you don't lose that much time really. So, and for the implicit information transfer, you not always, but quite often you need the single trial activity. You need to know, was there an error now, or was there no error now at that time, and not in, I cannot repeat that, right? So there's no chance. So that's why our approach is, we don't avoid explicit interaction. So that's not the case, but what we try is to focus on spontaneously evoked brain activity, and that's very important. So activity that's evoked because we see there is an error, or activity that's evoked because we see there is a very task relevant information given to me and I have to do something on that, and that can be read from the EEG. We can also use this brain activity for controlling a device. So, but this is kind of a mixture between explicit and implicit. So just by the embedded brain reading, I would say it's in between. So for example, if you were an exoskeleton and you want the exoskeleton to support your movements, you think, or you try to move your arm, and you automatically, of course, think of moving the arm. That's recorded. And then the exoskeleton then helps you to move the arm. And then you can discuss, is this implicit or explicit, right? It very much depends on how much you really think of moving the arm and how less you do this. So this also depends for patients. Maybe they have to think really hard and imagine this arm movements very hard to evoke the signal. But usually, it's in my opinion, it's more implicit. But that's why we put it in between, because we have lots of discussions on that, which category the individual signals are. So, but this is quite clear. Just to give you an example for what we don't want to do, this is an explicit interaction. So this is also in BCI. You can see it's wearing a cap. And this was a student project in our lab, and they tried to guide the robot, or in this case, the simulation, through a lab and through a corridor, a room. And you can choose the arrows where to go: forward, right, left, fast forward, or only one step forward. And that's just when the errors disappear, then you have an activity in the brain that we recognize also in single trial in this case. But I would say you can use an eye tracker, right? So this is very much like we're using EEG data as a control signal, but it's very artificially used in this case. So that's what we don't want to do. So now I wanted to give you some examples how to solve some of these issues that I came up with. Oh no, first I want to give an overview on some special challenges, and then I want to give you some examples. So what are the special challenges? So one is, of course, noisy data. So especially in applications, we have even more noisy data, and that makes it more difficult. And here we often have to combine different psychophysiological measures to be more accurate in our predictions. Then we have a lower performance in detecting specific conditions compared to a lab condition, right? So we know that our performance will be not as good as under lab conditions, under controlled conditions, and we have to see how to use that to adapt the system safely and control it with this very uncertain data. And the other thing is, when we go into applications, then we don't have many training data. So it's very expensive to have data acquisition in a complex application. And we don't usually have sufficient training data, and that has to be handled as well. And I will give some of these, some examples here how to solve that. So how to combine different psychophysiological measures. And now I go with the Lipid Experiment. So this is the Lipid Experiment actually recorded in our lab. So what you see here is a person sitting in front of a monitor, and it can see the little animated puppet or doll or whatever you want to call it, right? And we record brain activity and muscle activity. And this is green is brain activity, red is the muscle activity. And whenever we detect movement and tension in the brain activity, the doll is moving. When we detect it in the muscle activity, the doll is moving depending on what we present to the user. And we also have this combination. The combination is always good to make the prediction more safe, right? So, and this is the little video, and you can see that the puppet is moving definitely before the person, right? You can see that, and that's very strange. I mean, it's really strange to the person in front of the PC because all the subjects try to stop their own movement. So it was all too late, right? Because you already decided to move and you cannot stop it anymore. So what you feel is, when you see that, you feel like someone else is controlling you completely. And that's really bad, because if you were an exoskeleton and the exoskeleton would move your arm that early, you would have not the feeling that you do the movements, but the exoskeleton is actually moving you, right? So, and that's really weird. We tested it only with one of my colleagues, and he said he will never do that again. It felt really, so that's why we said this is not a good way, because we can optimize our prediction scores such that they're just predicting the movement just before the movement onset, but it's really hard. And that's why we said we have to combine. So in this case, we said we combine this brain activity with muscle activity, because even after stroke, the person, they have some little muscle activity left in most cases. So you can detect the movement intention in the EEG. And then when there's a little bit activity in the muscle, then you say, okay, now we start the movement. We know already that there's a movement that is planned, and then we only use this trigger to start it. And this is one of our older systems, and this is when we tested this the first time. So we combined EEG and muscle activity together with an eye tracker. Because eye tracker is also important, because we only want to move the arm when we look at an object that we can reach and touch and manipulate. That's also important. So whenever we look somewhere else, then we ignore the brain activity and the muscle activity, so to say. So, and we also distinguish between right and hand arm movements. And the thing is, again, we say if you have a movement that you want to perform, then you plan it. So you need corresponding brain activity. So we look for the lateralized readiness potential here for right and arm movements. And then you need also the person to really want to execute the movement. That's also important for the patients, because if you only control the system with brain activity, they stop trying to move themselves. So they really rely on a system at some point, and they just say, okay, I can just think of that and the system is doing that. But that's not what we want. We really want them to try themselves. And all the analysis, you just saw the combinations is done on this little board. So that's the embedded solution where we do the brain signal analysis on. Yeah, so when we combine it differently, as you can see here in the lower part, on the right lower part, you can see that when we combine both systems in an AND combination, saying both signals must be there, then our true positive rate. So when we're very sure that the person wants to move is very, the false positive rate is very low, but the true positive rate is not that high. So that's the drawback. But when we have an OR combination, an early rehabilitation, where the person is very weak and we are not so certain about the signals and the condition, so then we can combine both signals in an OR combination for the start of the rehabilitation phase to have better motivation. You can see in an OR combination, we have a bit higher false positive rate. So when the system starts the movement, but there was no movement intention, but we have a very high true positive rate. So that means whenever the patient really tries to move, then we usually detect it and we can control the system respectively. So that's also interesting that you can combine it in such ways. So then how can we adapt machines safely with EEG data? This is another example. So here we have again a different exoskeleton for teleoperation, and you teleoperate this robotic system in a different room, and what you can see that in VR. So this is what you can see. And what we want to do, we want to support the teleoperator. So that's not a patient, right? It's a healthy person. And we thought, so how can we support the teleoperator? And that we can do because the exoskeleton, when you do a manipulation somewhere in the air, so the robot you have to keep your arm steady in the room, somewhere in the 3D room, so to say, then the exoskeleton will recognize that and will keep your arm there. So you don't have to hold it by yourself, but the arm will be kept there. So, but then the system doesn't know when the person wants to move again. That's the problem. So for that, we have sensors in the system, 4 sensors. And then when you try to move, then the source sensors will recognize that, and then you can move freely again. But you always feel that the system is not transparent. You have to move against the system for a certain time. And at that time, we looked at the EEG. And this is so to say the online prediction score. So that's the prediction score for the detection of the lateral readiness potential. And you can see that it goes the blue line, right? It goes pretty much up before the movement. The movement was the yellow line that will be shown in a second again. So here you can see that the probability that there is a movement intention goes up, and the yellow line shows where the system starts to move, where the person starts to move. That's the yellow line there. And what do? We actually use this prediction score to adapt the force sensors. So the force sensor sensitivity. So whenever the prediction score goes up, so there's a higher likelihood that the movement will start, the force sensors get in the system become more sensitive, so to say, and then it's more easy for the user to unlock the system, so to say. And we could see that since we do this prediction every 50 milliseconds, that even with the noise and the data and everything, we could avoid unwanted releases. And in general, we could improve the transparency of the exoskeleton. So this is a combination of different signals. So in this case, the EEG signal, which is the covert signal that we record and analyze, and we combine that with the overt behavioral data that you can observe, but also that the exoskeleton can easily read out. And by this is one of the approaches where we can assure inherently safe behavior of the system using such data. And now you might wonder, so how exactly did we adapt it, or how did we? What was the approach? So when you classify your data, you have, in our case, you have two classes. The one class would be there is movement intention planned, so there's a lateral readiness potential in a signal somehow. And on the other hand, there is no movement intention, so there's not such a signal there. So these are the two classes. And so you train a classifier on that with examples that are, of course, predefined and known, that there are movement and non-movement class data. And then you look for the distance of the examples from the SVM hyperplane. That's the hyperplane that's separating both the classes, so to say, best. And this difference we transfer into so-called prediction values. So we have, the further they're away from the hyperplane, the more sure we are that this is either a movement or a non-movement class example. So we transfer that into a SVM prediction score, and this prediction score we map to a sigmoid fit. So and then after this mapping, we could use this information to adapt the force sensors. So that's how it was integrated, and we actually thought, okay, we have to check whether this really works. And now you know that this is very hard to test, because the classification will change all the time, and you cannot ask, was it better than the other thing? So what we did is actually we simulated the adaptation with this system. But first of all, we actually calibrated the exoskeleton, because you can imagine if there is a big person in the system, it's stronger. So it's more easier for this person to unlock the system by pressing against the force sensors. And so we first of all, we calibrated the system to the user, so that we had an optimization of the sensitivity of the force sensors in time as well as force. And then with after this individual optimization, we actually adapted this value, the sensitivity value, based on the on the predetermined value from the expected SVM score from the classification. So we had one middle adaptation and one adaptation that was kind of in case 100%, in case you were 100% sure that there's a movement, and something in between. And then we asked the person whether they would feel these differences on the one hand side, and we would also measure the difference in the force sensors themselves. So we can actually measure the force that was applied by the person over time to see how hard it was to unlock the system. We could show that there is a significant improvement in the interaction behavior between the human and the system itself. So the exoskeleton in this case as an interface. So, and finally, I want to show you, this is again a different view on this, on the same thing. And what you can see here is, as I said, we do this prediction every 50 milliseconds. So is there a movement or not? And this chart shows you at 0 on the right-hand side, this is where the movement starts. And all the values before are actually prediction scores from 1000 millisecond windows. So we have a sliding window approach where we look for 1000 millisecond EEG data, look whether there was a movement planned, yes, no, and then we slide for 50 millisecond and so on and so forth. So you can see this the prediction score developments over time, right, as a mean, I think it was. And you can see that you have, when you train, depending on which window you choose to train the classifier, you get different results. So you can choose a training window for there is movement intention, which ends 400 milliseconds before movement onset, or you can use a window that ends 150 milliseconds before movement onset, for example. So we need to get this movement intention example. Movement preparation example, and you can see that the values are different, and in the end we decided in such a scenario to choose a window that ends 250 milliseconds because then the values were best, and from the timing it was, in our case, was the best window to train a classifier on. So that's also very important to decide which examples you train your classifier on. So not only the examples, are they good or not good, but maybe examples in time in this case when there is a development in brain activity. And finally, you might also know about BCI illiteracy. So some people are not performing very well in such BCI scenarios, I would say. It's general brain-computer interfacing, right? So it's hard to analyze their brain activity. And you can see here 4 examples. So 4 persons who tested the final system. And you can see that one of the person achieved a very, in comparison, a very bad performance of 0.75. compared to 0.83 or 844 around that time, right? And what we did is we did not give up, but we said, okay, we already tested different windows, so maybe there was different for this person. So we said, let's combine different windows. So what we did not only train on one window, but we choose 2, 3, 4, 5, 6, 7, 8, up to 13 overlapping windows for training. So we combined artificially, kind of enhanced our, extended our training data, so to say. And already when we combined only 2 windows, you can see that the performance was massively increased for this person, right? So it was also increased for the other persons, for the one that are already behaving very good in performance. But for this person that was really bad at the beginning, it was much improved by combining 2, 3, or 4 windows. Then later you see it also gets worse again. So it doesn't help always to take all the data to train on. So you have to select properly. So this is also important. Now for the last thing. So this was already something that tells you how to get more training data. In this case, it was one example, but I want to give a last example of how to generate more training data when you're in an application case. So when we have a patient who wants to move, or who is in therapy, or who wants to use the exoskeleton, especially when he does this in a guided fashion with a therapist, it's very important for the therapist, especially after stroke, that the person really understands what the therapist wants her or him to do. So it's not only that after stroke you have problems with moving your arm, but you also have some cognitive deficits. So, and you cannot concentrate very long. So it really doesn't help to do the training or the therapy when you're not concentrating on the task, because you don't train the bodies and the arms, you train the brain, right? And when you cannot concentrate anymore, then the therapist usually stops the session and says, okay, let's have a break and we do this later again. So, and we also developed an approach, and that was actually also in teleoperation, where we could recognize from the brain activity whether the person who is controlling a robotic system recognizes important messages. And that's very important, because in teleoperation, as you saw before, you're very much concentrated on the system, and when there is a warning or some other task showing up, you cannot see that. That's the same example with the gorilla running through the screen, right? And you do not recognize that. So, so we developed an approach that actually allows us to detect and single try whether there is a task relevant information showing up. And this task relevant information has is correlated with target recognition. So it's a target, right? So you have to respond to that. And also to task coordination, because maybe you have to concentrate on what was asked from you. So you stop doing whatever we're doing, you do something else, right? And this is, I don't think I have the time now. I have some slides, but I have taken it out. So I think, and I believe this is, or what our research showed is that in such situations where you do something else and then you have to respond to other tasks or other warnings and so on and so forth, then you do not only get a P300 that you probably know, but you also get kind of a perspective positivity. That's something that makes you to change your behavior, to do something else than what you're just doing, to remember what else you should do when this question was shown to you. And what was the scenario? So again, when we try to develop, or not again, but when we try to develop an approach, we don't go already in a situation to train that with the robotic system. So now all the examples were with robotic systems. So, but we also sometimes develop some scenarios in a more controlled condition. So, and what you do in collaboration or when you do fine manipulation, whatever you're doing, you can simulate that, for example, with such a labyrinth game, where you control a little ball through a maze, and that's very hard. And you can also bring this in VR. So this was the setting. We did that in real as well as in VR. That was a VR setting. And you would look at the game and you would try to balance the ball through the game without falling in the little holes here. There are some holes. And at the same time, you get some information just in a symbolic fashion, presented in the same scene, so to say, in a head-mounted display. And there was some information that had a small corner on the sides, and there was information that had longer corners on the sides. So whenever the corner was longer in comparison, you had to press a buzzer. So you had to stop playing the game and press a buzzer. So what happens then is that you will receive a so-called, I just called it P300 now, but it's a combination of P300 and perspective positivity. And but the point is, when we talk about this, in our scenario, so in our situation, we had 6 subjects playing the game, and all the subjects did 10 runs in 2 sessions. So they did quite a lot of runs, and the target standard was 1 to 6 in a random order. So it was quite high. Usually do 1 to 8 or something like that. So we wanted to have more target examples, of course. So we stressed that a bit. So that means we did quite some experience, so lots of experiments to get this average activity here. So this is an average activity over 1,623 targets. So this is after artifact rejection and so on and so forth. And we had 439 examples for missed targets. So when you did not recognize that you had to respond, that's the blue line, right? So you just didn't see that there was this larger corner, so to say. And this to get only 439 examples took us 10 hours pure recording time. That's without preparation or anything. That's the only recording time, and that's only 3 sessions out of the 10 of the 5 subjects. So this is quite a lot of data, and you can imagine you cannot do that in an application, in a real application. That's no way how to do it. It's even here, it's hard, even with 400 examples, it's hard to train a classifier on that. So with on one subject, usually you don't train on 5 subjects, right? You train for 1 subject, right? So you can imagine that the 439, you have less than 100 examples for 1 subject in the end. So what did we do? We actually thought of, let's look into the signal again, and what else could we use? And we also had those standard events where the person had not to do anything on them, right? With the smaller corners. And then we said, okay, from the ERP that they would evoke, they're very similar, as you can see, to the missed targets. They're very similar in shape. And that's why I said, well, why don't we train on targets and standards instead of the missed targets and the targets for a classifier and see how well this works? That's actually what we did. So we always trained on, the one class was the target class. There was always a class, the target that were responded, so recognized as a target, and the other class were in the training, the standards, right? So the ones that were not relevant actually. And later in the test phase, we actually used this classifier that was trained on target and standards to distinguish between targets and missed targets. So we kind of did a classifier transfer between those classes. And we could show that this is again an ERP of one subject. And we looked again for different windows as we did before, where is the best possibility to transfer it. And we could see that in the middle window of this whole activity between 300 and 600 milliseconds, we could see at least, so there was really no statistic difference between the ERPs evoked by standards and missed targets. So, and then we choose actually this window to train a classifier, and this is again a different view. So again, now it's a bit, sorry, it's a bit different colors. So you have the standards in black again, the targets in green for whatever reason, and the missed targets in blue, kind of. And what we did the training on the standards and targets here, black and white. And we did the evaluation, how good is the classifier on the same signals. So you can see that we have a very good performance in classifying the signal. And then, but in the application or in the testing, right, we actually use this classifier that was trained on standards and targets to distinguish between missed targets and targets. And you can see that the performance is a bit less, so it's not as good as with in the other case, but the reduction was very, yeah, it was really not that bad. It looked worse from the colors than it was actually. So we could transfer that very well to use that in the application case. Okay, and that was my talk for today. Thank you very much for listening.